Hello, I'm John Rakovan from the Department of Geology and Environmental Earth Science at Miami University in Oxford, Ohio. Today I'd like to share with you some of our recent results on the origin and the nature of wire silver and wire gold. This is a morphology found in native metals, particularly of these two species, especially in silver. Wire texture metals have been known for centuries. However, only recently have we learned about how they form and the internal structure of these materials, and thought very fitting on Mineral Day to look at something that is hot off the press in terms of our understanding of some very unusual samples. Native metals such as gold, silver, and copper occur in nature as most minerals do, with faceted crystals. A much more unusual morphology found particularly in silver and rarely in gold is a wire morphology, or more rope-like depending on the size of the samples. Although specimens like these have been known for hundreds of years and adorn mineral museums and collections around the world, very little has been known about their crystallinity and formation until recent studies. Today's talk is a quick review of new insights into wire, silver, and gold formation and the nature of these unusual mineral specimens. I want to start by thanking my collaborators and funding groups. Calvin Anderson, a PhD student at Miami University, did most of the synthetic wire silver growth and isotope analysis, along with Ryan Mather from Juniata College. Looking at the wire golds from Harvard University was done with Raquel Alonso Perez and Frank Koich. Anton Tremsen, Sven Vogel were instrumental in the use of neutron facilities that will be mentioned in this presentation. Volker Luters and Thomas Bollinghaus independently worked on samples in collaboration with one of the funding groups, the Mineralogical Research Initiative. Most recently, we've got additional funding from the National Science Foundation, the Los Alamos Neutron Science Center, and the Japan Proton Accelerator Research Complex allotted us beam time for isotope analysis of the samples. This is an exceptional example of a wire silver specimen from the Himmelsfürst mine in Freiburg, Germany. It belongs to the Mining Academy in Freiburg and is probably several hundred years old. Freiburg, Germany, Kongsberg, Norway are examples of classic localities that are famous for having produced wire silver specimens. This one in particular is nice because of the associated minerals on the matrix. The wires are growing from silver sulfide, currently a acanthite, and the base matrix is limestone with calcite crystals. Other more recent deposits have been discovered which also produce exceptional silver wires, including Uchuchacua in Peru and the Yushan mine in Anhui, China. This is a beautiful 11-centimeter specimen with calcite crystals on it. Now, both of these are examples of wires that have grown in nature in hydrothermal deposits from essentially hot waters, but very little was known previously about exactly how such specimens grow. Interestingly, it has been known since the 1500s that if silver sulfide is heated, which is what miners do in the process of smelting silver ore, that silver wires will grow before the acanthite actually melts. This is a specimen of synthetic wire silver that was produced essentially the same way, but in the laboratory, where a natural piece of acanthite was heated in a Bunsen burner, and the wires that you see here grew. You can see that they're multiple centimeters in length. These grew within a short period of time, probably an hour or so. We've been producing wire silvers of synthetic nature in our laboratory by several different means, including the flame method, where you have a piece of silver sulfide in a thermal gradient produced by a Bunsen burner. Here we have a silver specimen on top of a chunk of acanthite, and it's being cooked with the Bunsen burner, causing the silver wires to form towards the heat source or up gradient. We can also produce silver wires, or at least the initiation of silver wires, in vacuum using a scanning electron microscope. On the left is an image of the SEM at Miami University, and on the right is an image of the growth or the incipient growth of silver wires under the electron beam. And this is done in an ultra-high vacuum so that we know that there's no environment other than the vacuum around the sample. The electron beam is causing silver to migrate towards the surface of the acanthite to be reduced and then to sprout as individual silver crystals or wires, which then coalesce to form an extended silver wire. As I had mentioned previously, in nature, this is not the method or the environment in which wire silvers are growing. They're probably growing from hydrothermal solutions, but also in the presence of sulfides like acanthite. And we've reproduced this in the laboratory as well using what is known as a bomb. We seal a liquid and samples of acanthite and other constituents in this metal container and put it in an oven, causing both the temperature and the pressure within the container to go up. And this is a SEM image of an example of a wire that has been grown hydrothermally in the laboratory. Now, based on all of the experiments that we've done, hydrothermal, in the flame, and in the scanning electron microscope, and analysis of the resulting samples, we have a model and a much better understanding for how these wire silvers are growing. First of all, the texture of the wire silver, which previously had not been fully understood, is comprised of multiple small single crystals over which the striations are superimposed. This is a scanning electron microscopy image of the end of a wire silver that we synthesized in the laboratory. And notice the alligator type texture, the alligator skin type texture on the surface here. If we circle one of these grains, these are individual silver crystals. And you'll see that there are many of them comprising the entire wire, and the striations don't correlate with the individual crystals at all. They're just superimposed on this polycrystalline texture. Now, this was observed also in the interior. On the left is a reflected light image of a natural wire silver that has been cut and polished, and you can see all the grain boundaries in here. And on the right is a type of diffraction imaging called electron backscattered diffraction. And this is an orientation map where essentially each color represents one of the grains within the wire silver. This is a natural specimen as well. This was published in Bollinghouse et al. In 2018. And what you can see is the same sort of texture that we see in the reflected light image here on the left and the previous image of the surface of the synthetic wires. In all cases, wire silvers are comprised of multiple single crystals that aren't very elongate whisker-like crystals, but are more equant with a slight elongation and potentially slight preferred orientation along the wire direction. So our hypothesis, based on all of these observations for how wire silvers are growing, has to do with a very unusual property of acanthite. Although acanthite is a solid, silver ions can move through the solid at rates that are much, much greater, orders of magnitude greater than normal diffusion. And this process is known as ion conduction. Now, actually, it turns out that acanthite is not an ion conductor, but when heated, such as in the laboratory experiments in the Bunsen burner, above 130 degrees Celsius, the acanthite turns to argentite, and argentite is an ion conductor. In fact, it's a superion conductor. It has the greatest mobility of any known ion conductor, natural or synthetic. And so our model for what is occurring, based again on all of the observations and characterization of our synthetic samples, is that we start with acanthite, silver sulfide. When that is heated or put in a thermal or electric gradient, what we find in the SEM, we start to convert some of the acanthite to argentite, the superionic conductor. And that allows silver ions to migrate very rapidly to the surface of the argentite, where the silver is then reduced and crystallizes out as native silver or metallic silver. Now, the rate of migration or conduction is so fast that as these atoms organize themselves on the surface, many defects are created within the crystals, and those defects are essentially grain boundaries. So this represents one crystal here, and there's another crystal here, and we believe that it's the rate of ion migration and the formation of the wire that leads to the polycrystalline texture. Now we can see in the SEM image that when the acanthite, which is the background material here, turns to argentite, there's a slight increase in the volume, and you can see that by the formation of these pedestals. And then forming on top of the pedestals are the initial sprouts of wire silver. Now, individual sprouts will start to grow and then coalesce and eventually become a large wire like the one that we see here in the schematic and the image that we see on the upper right. Now, again, the striations that occur are essentially superimposed on this polycrystalline elongate mass of wire silver. And those striations continue down all the way to the base of the silver sulfide, where the actual crystal growth is taking place. So crystal growth in the case of wire silver is at the interface between the wire itself and the matrix or the acanthite. And atoms are moving up from below as they are conducted through the acanthite and attached to the bottom. The wire then is translated out away from the matrix, and whatever the footprint looks like, that is the shape of the original argentite footprint, that is translated as the wire is progressively added to at the base, and that's what forms the striation morphology on the surface. Now you can tell from the previous images and this one here that the characteristics of both the natural and the synthetic wires are almost identical. In fact, here's a specimen on the left is a natural wire silver on acanthite from Hongda, China. And on the right is a synthetic wire silver on the exact same acanthite that we grew in the laboratory. And the morphology, the internal texture, all are identical, which is very interesting and suggests that even in hydrothermal conditions in nature, wire silvers are also growing by the same method, that is the ion conduction through acanthite or the high temperature polymorph argentite. Interestingly, silver has two natural isotopes that are stable, silver 107 and silver 109. Now, isotopes are atoms of a particular element. In this case, silver is defined by having 47 protons in its nucleus. So both isotopes have 47 protons, but the number of neutrons is different. Silver 107 has 60 neutrons, adding up to an atomic number or atomic mass of 107, and silver 109 has 62 neutrons. So 47 protons and 62 neutrons adding up to an atomic mass of 109. These are roughly similar in abundance in nature, with 107 being slightly more abundant. Not only did we analyze the growth mechanism, texture, and crystallinity of the wires, both synthetic and natural, but we also looked at their chemistry, and more specifically, their isotope chemistry. The data that I'm going to show you are given in Del 109, and this equation describes what those values mean. Essentially, it is a comparison of the ratio of the 109 to 107 isotope abundance in a sample compared to the same ratio in a standard. Now, in the Del value, if the sample and the standard are identical, the value will be 0. If the 109 or heavy isotope is enriched, the value will be positive, and if the 107 or lighter isotope is enriched compared to the standard, then the value will be negative. Here we have a plot of the del value. Remember, if the sample and standard have the same 109 to 107 ratio, the del value will be at 0. If 109 is enriched, it will be positive. If 109 is or 107 is enriched, it will be negative. And what we find if we look at silver isotopic composition of acanthites from many different samples around the world, native silvers that are not of the wire morphology, and other samples including smelted silver and silver as an alloy in gold samples, there is very little variation among the medians of the isotopes for those different types of samples. However, natural wire silver, that is a morphology that is not described above, has a slight enrichment compared to the others with respect to 109. Now this is very interesting. All known mechanisms of isotope fractionation, that is the enrichment of one isotope over another, in nature would predict that the light isotope, that is 107, would become enriched, and it would not be more positive, but the del value would be more negative than the gray line here. And we see that indeed it is more positive. What we think we've stumbled upon is a previously unrecognized mechanism for isotope enrichment or fractionation in nature. Now, more interestingly is if we compare the results of our synthetic wire silver experiments. Now, those that were grown by the hydrothermal method at lower temperatures, 130 to 180 degrees Celsius, show similar values to natural wire silvers, although we don't have many analysis points there, so that there's not a good comparison. However, the synthetic wires that are grown in the flame, in the Bunsen burner that I showed you previously, show an order of magnitude enrichment in 109, indicating that this enrichment process is indeed real and that we believe is reflected in the environment, exact environmental conditions when the silver is being produced. Now we have a hypothesis for the origin of this fractionation, but this is something that we're trying to experimentally test currently. If you're interested in the results of all of the things that I've discussed here, including the growth of wire silver, the texture, and the isotope fractionation, this has all been recently published in a paper in the journal Geology titled Natural Solid State Ion Conduction Induces Metal Isotope Fractionation. And this is in the July 2019 issue of Geology. You can see the cover image is a wire silver specimen and calcite from Kongsberg, Norway. It's a classic location for wire silvers. As mentioned previously, gold is also, but much more rarely, found in the wire morphology, and so a natural extension to our work would be to look at the mechanism of growth of wire golds. Because of the work we had been doing, I was approached by Raquel Alonso Perez and her colleague Frank Koich, both from Harvard University, to look at one of the most famous and finest examples of wire gold in existence. Known as the ram's horn, this 12 centimeter tall exquisite example of wire gold is from the Gilman district in Colorado, specifically from the Groundhog Mine. Its provenance is well established because several articles were written in the late 1800s and published both in a newspaper and in a scientific journal once the specimen had been uncovered. To look at the crystallinity of materials, the standard methodology is X-ray diffraction. However, because gold is so dense, X-rays only penetrate the very surface. And if we want to look at the interior, we would typically have to cut samples like this open. However, because of the great value of specimens like the ram's horn, we can't do that. Instead, we had to turn to a different technique. Instead of using X-rays to probe the crystallinity of our samples, we turned to neutrons. Neutrons are very penetrating and can go through an entire sample like the ram's horn without having to cut it open. Neutrons will both diffract and adsorb in ways that give us information about crystallinity and chemistry, both the elemental chemistry and the abundance of different isotopes of the elements that are present. To do this, we turn to the Los Alamos Neutron Science Center in Los Alamos, New Mexico. This is an aerial view of the facility. The mountains in the background are the Jemez Mountains, and we're on one of the several mesas where Los Alamos National Laboratory is located. The facility includes a proton storage ring, a linear accelerator along which protons are accelerated very close to the speed of light. They're then diverted and shuttled over to the Lujan Scattering Center where they impinge upon a target. That target then breaks up into small particles of protons, neutrons, and other subatomic species, and we use the neutrons for our diffraction and spectroscopic measurements. Because the experiments we were doing had never been applied to similar samples, we analyzed several different mineral specimens to compare to the Groundhog Mine gold wire. One was a silver sample of similar size, and since we've already studied silver extensively, we know what the texture of the interior is like, and so we can better interpret the neutron data and then compare that to the data that we get from the groundhog specimen. We also looked at another wire gold specimen from the state or the country of Colombia. This was found in a placer deposit. It had formed hydrothermally in some environment, weathered out, and then was deposited in a sediment in a stream, and we extracted that to look at its crystallinity and texture. Before taking the samples to the neutron source to do diffraction and chemical analysis, Frank and Raquel looked at the samples in a scanning electron microscope and used energy dispersive analysis to analyze their chemistry. Now, the electron beam, just like an X-ray beam, only penetrates the very surface, and so these results are telling us information about the surface of the samples, but not their interior. Interestingly, the wire gold from Harvard, the groundhog specimen, shows an appreciable amount of silver. Calculated intensities give us about 30% silver and 70% gold in that specimen. The Colombian wire, however, is about 100% gold. There's no detectable silver. In this spectrum, the iron and silicon are due to contamination of other minerals on the surface of the sample. After doing scanning electron microscopy and EDS analysis, we flew down to Los Alamos and did the diffraction and spectroscopy experiments at the Los Alamos Neutron Science Center. We're going to start by looking at the data from the wire silver because we already know about the texture and crystallinity of such samples. This is the sample that we analyzed for comparison. It's similar in size to the wire gold from Harvard. The take-home message here in these data, without getting into the details of what they represent, is very simple to interpret. If we see long streaks of diffraction data, such as the red lines in the diffractograms up here, that represents a sample that is made up of many, many individual crystallites, and that is consistent with what we saw in the studies of wire silvers previously. Very surprisingly, however, the diffraction data from the wire golds look very different than from the wire silver. We see individual diffraction spots in red and yellow here, and this suggests that although the morphology, the exterior texture and morphology of these look very similar to the wire silvers, the interior texture is much more like a single crystal or a few large crystals rather than being made up of many hundreds or thousands of small crystals, as are the silver wires. We get the exact same result with the Colombian sample, indicating or suggesting that this is a characteristic of wire golds that is very different than the wire silvers. In addition to analyzing the crystallinity, we wanted to look at the chemistry of the samples. And to do this, we used energy resolved neutron imaging and resonance spectroscopy. This technique allows us to penetrate the entire sample and get information about elemental abundance as well as isotopic composition. The neutron spectroscopy shows that the entire volume of the Harvard sample is 30% silver and 70% gold. This is consistent with the EDS analysis of the surface conducted by Frank and Raquel at Harvard University. Interestingly, however, we get a very different result for the Colombian wire gold. EDS analysis tells us that it's pure gold. However, the resonance spectroscopy, which looks at the entire volume, sees 25% silver and 75% gold, and that actually is not surprising. We know geologically that gold samples alloyed with other elements, if they sit around in placer deposits where they're exposed to groundwaters for a long time, the surfaces can leach the impurities and become enriched in gold. And that is exactly the type of environment that that sample had been discovered from. And so our result is consistent with what had been previously determined about the chemistry of placer golds. Thank you for listening to this presentation. I hope it was of interest and you discovered something new about this really unusual morphology found in native metals, particularly wire silvers and wire golds. If you have interest in the wire silvers, as I had mentioned previously, you can look to the journal Geology in the July 2019 issue. If you want to learn more about the wire gold study, and in particular the groundhog specimen, National Geographic did a very nice online report of our work. Search National Geographic and wire gold and you'll get to those results.